Next, we have Stefano and Fabrizio joining us, who will be talking about how category theory could potentially be used to simplify the complexity of quantum circuits. And I guess, as a piece of context, I think Fabrizio and Stefano are maybe like the first people who have tried to bridge the quantum and crypto world, and they've been doing so for several years, and like finally are starting to break through. So looking forward to your talk.
Cheers. Thanks. Okay, so this is a gentle introduction to ZX Calculus. A spoiler alert, it won't be gentle, sorry. Basically, the reason for this is the following. Several years from now, hopefully someone will say, okay, I have a quantum circuit that realizes a one-shot signature. I have just one problem. I use 1 billion T-gates, and the feasible threshold is like 10,000. Can you make it work? And we need a framework to simplify these circuits to make them hopefully more implementable. And the way we can do this is via using graphical calculi. So what are graphical calculi? As the name suggests, they are things that allow you to do math pictorially. They derive their formal strength from something called category theory, which I'm not diving into. And they have been applied to various fields, functional programming, linguistics, linear algebra, and a lot of other stuff, but most importantly, quantum computing. Okay, so very quickly, that thing on the right is a wire, and that represents a system of sorts, a system of type A. This is a process, it's just a box that takes things of type A and spits out things of type B. For every type, we have an identity box, a trivial process that doesn't do anything, basically, and for that reason, we do not draw it. Boxes can be composed. I don't know why the wires don't show up here, but basically, if F and G have matching inputs and outputs types, you can plug them together. And only topology matters, meaning that the only thing we care about is how these things are connected. You can move them around, that's not a problem. And indeed, that's exactly how we manipulate these graphical calculi. We can also consider systems in parallel, and the way we do it is by just taking wires in parallel, unsurprisingly. When we do that, we have a system that swaps the places, or a process that swaps systems places, basically. So A, B goes to BA. We have a trivial system that, again, we do not draw. Processes can consume multiple systems and spit out multiple systems. And we can also compose them in parallel. So in this case, basically, F and G are acting independently on two different systems and spitting outputs on two different systems. Then we have some equations. So for instance, if you swap these things twice, you can yank the wires and get the system on the bottom. And again, this, I think, looks very intuitive. If F and G are acting independently, you can slide one past the other, basically. OK, so example, sets and functions. Now we can basically say, this is just a set. Now our systems are just sets in this example. These are just functions. This is the identity functions that maps every element to itself in a set. This becomes function composition. This is the Cartesian product now, so it's just couples, basically. The swap is just swapping couples at this point. The trivial system is the singleton set, and indeed, if you do the Cartesian product of everything with the singleton set, you get the thing you started with. So that's why we don't draw it, basically. And parallel composition is just functions acting component-wise. Okay, so why does this work? There is a very deep theory in category theory that basically says that this calculus is logically sound and complete with respect to something called free symmetric strict monoidal categories. Sound means that basically whatever we can prove graphically can be proved in these categories, and complete means the opposite. Whatever can be proved in these categories can be proved graphically. Okay, so basically now the point is sets and functions form a category that is basically a free symmetric strict monoidal category plus some other equations. This means that our graphical manipulations will always make sense when you interpret them as functions and sets, but there are more things that you can prove in functions and sets that will not be provable graphically because you need more graphical equations. Another example that gets closer to ZX calculus is finite dimensional Hilbert spaces on the complex numbers. So in here, we say that a system is a finite vector space, finite dimensional complex vector space. A process will be a linear map. This is the vector space tensor product. Now the trivial process is the field, is the base field C. And indeed, if you tensor something with C, you get the thing you started with. But now we also, oh, this is all garbled. It wasn't like that when I sent the slide, I swear. But basically, this weird wire here is called a cup. And what it does is, it goes from a vector space tensored with this dual to the base field, that again is the trivial wire we don't draw. And the way this works is by just taking the scalar product of basically a vector here and a vector here expressed as bras and cats, and you just take the product. This does the opposite. It's basically sending a complex number to the complex number that multiplies that process here. That is just the tensor of the bra and the cat. But now the funny thing is that you can pipe these together. This is all garbled now, unfortunately, but basically, when you do the calculations, what happens is that you get the identity. Because you take a vector, then you are basically sending this vector to itself, tensored this thing. Now you are taking the scalar product of this and this, and keeping this. Now this is the Kronecker delta, and you get back what you started with. So in the end, we have another graphical equation that is called the yanking equation that basically says that you can yank these things. Okay, so now we can talk about the ZX calculus. That is basically this kind of thing on steroids. So basically, there is a very important result that says that the calculus I'm going to show you is sound and complete with respect to complex finite dimensional Hilbert spaces of dimension 2 to the n. That is basically qubits. So what it means is that whatever you can do algebraically on qubits, you can do graphically. Okay, so this was originally proposed by Bob Kuke, that was my former PhD supervisor, and Ross Duncan in 2008. It took a lot of time to be developed and for completeness to be proven. And now both Bob and Ross work at Quantinuum, and this is one of their flagship products, basically. So, okay, before continuing, remember that computation in quantum computing are made in a complex vector space as finite dimension 2 to the n. Caveat, you can use density matrices and other stuff. We can do that as well graphically, but I'm not going into it. So for every qubit, we use two bases that are called the computational bases, and it's denoted as 0 and 1. And the Hadamard bases, that is denoted by plus and minus, they are related by these equations. Okay, so the main ingredients of the ZX calculus are called spiders. We have two types of spiders, red one and green one. And a spider has a finite number of legs on any side. This spider here basically is this function. So we are taking n zeros in the computational basis, and we are spitting out m zeros in the computational basis. We are doing the same with ones, but we are multiplying this by a phase alpha that is shown in here. And the red spider does exactly the same thing, but in the Hadamard basis. Okay, so first things first, we can specialize these spiders. So if we take the ones with zero phase, when the phase is 0, we just don't draw it, with 2 legs. This guy is this guy is this. These are the identity functions expressed in their respective bases, so that's the identity. Similarly, you can prove that these things become caps and caps when you have a 0 phase. If you take a p phase, then basically you get the Z and X poly matrices. These are what is written there, these pictures. And you can represent the Hadamard gate with this monster that I will never use, and I'll just use that syntactic sugar there. And every ZX diagram is made only of these things. Okay, so what are the rules of the ZX diagrams? The first rules is that the spiders fuse. This should be a beta here. But the idea is that if I have an alpha spider and a beta spider of the same color, I can fuse them and I sum the faces there. The second equation says that I can turn a red spider into a green spider by Hadamarding all the legs. This one says that if I have a P face of one color and an alpha face of another color in this configuration, I can slide it through, and this thing here changes sign. And this says that basically the green spider acts classically on the red spider, and the vice versa is always also true. So basically, when I have the zero faces, you know, this green thing acts by copying the red thing. This is the second to last rule. It's called a bialgebra rule. It's basically saying that if I have all spiders of one color here and all spiders of another color here, and they are all connected to each other, I can slide them past and obtain this thing here. And the very last equation says that spiders of opposite color really don't like each other, and if they are connected by an even number of wires, you can chop them down. So every time they are connected by 2 wires, you can remove these 2 wires. And if you apply this recursively, you see that this can either be connected by 1 wire or by no wires at all. Because if I have like 3, I can remove 2. This is everything you need. And using these definitions, you can basically, using these equations, you can basically prove everything that you do with algebra by manipulating these little things. And it's very, I mean, one direction is not that surprising. Like if you take these spiders, you map them to the interpretation I give you in the beginning, and you verify the equations, you know, you write down the matrices and everything. It's like, okay, it makes sense that sums can be that phases sum when spiders fuse and whatever. But the opposite is really surprising. The opposite is saying that every algebraic manipulation in the vector space C to the 2 to the n can be done graphically. So why would I care about all this? The reason why this is really awesome is that now we can translate quantum circuits into decorated graphs. And when we do that, we have a rewriting system for simplifying quantum circuits, and we can apply the last 50 years or so of research in graph rewriting to simplify quantum circuits. So we can use double push-out rewriting, sesqui push-out rewriting, AI-based rewriting, whatever you want. So let me give you an example. These are 3 C-knots connected in series in this way. Let's translate this in a ZX diagram. This is the equivalent ZX diagram. So what can we do with that? Let's flip the last thing. Again, only topology matters in this diagram. So I can flip the last part as long as all the connections are the same. So I get this one here. I just flipped the third one. Now I can apply the bialgebra rule here and basically slide the red spiders through the green spiders, and I get this. Now I can apply spider fusion above and below. I get this. Now you see those spiders don't like each other. I chop their legs, and now these are identities. So basically, those 3 C-knots are just implementing a swap. Another example, this was also in Elam's talk. This is quantum teleportation. And I want to verify that quantum teleportation is actually quantum teleportation. How do I do that? Well, translate this to Spiderland again. This is the corresponding circuit. By the way, this is Alice's side, this is Bob's side. In here, Alice and Bob are separated by a red line. So what happens is that these 2 red spiders here are representing measurements. And these B's are Booleans, depending on the outcome of measurement that can be 0 or 1. Now, the whole idea of quantum interpretation is that after Alice has measured, she has to phone Bob and basically tell Bob the outcome of the measurement so that Bob can perform a quantum correction on its side, And that's exactly why this B0 is this B0 and this B1 is this B1. We are representing the fact that the classical information is being transmitted. Okay, so spider fusion here. First step. Hadamard changes the color of spiders. So we have this, fuse again, fuse again, fuse again. Now you see that this is 2 B1 pi. B1 can be either 0 or 1. So that thing can be either 0 or 2 pi. 2 pi is 0 because phases are periodic. So the phases goes away. And now you see we can simplify this because if you remember, spiders with no phase are identities. And now I can fuse again. I do the same thing. Boom, quantum teleportation. I can prove that I have a quantum channel between these two things. So we started with this thing, which if you show to me, I'm like, what the actual fuck? I mean, if you are not into quantum, it's difficult to grasp. And then with merely topological rewriting manipulations, we get to this picture, which is very insightful and very simple. And now the idea is that you can do this with every quantum circuit. You translate into ZX diagrams, you apply these rewrites, and as long as what you get in the end is a quantum diagram, you know that that is equivalent to the one you started with. So you can use this thing to simplify things. You can put weight on gates, for instance, and you say, can I rewrite this in a way so that I have as little T gates as possible? And so simplify the amount of quantum resources that you need to run these things. And that's it from my side. And then I'm passing it to Stefano. Cheers, thank you.